power series and functions. It's chapter 11.9 in the, I forget what textbook, but it's chapter 11.9. We'll try and do all of these. Quite a few, some of them not necessary, but we'll try. Okay, so we'll begin with these first two. Okay. So the first two rely on the same fundamental concept, but we'll go over the first one. So it asks if the radius of convergence of the power series, we'll write it out, 0, infinity of c of n, x of n, has a radius of convergence of 10, x is between, then what happens to the radius of convergence when you have this function, right? And look at the other one at the same time. When you have this series, and then you have this second series, what can you say about the radius of convergence? Okay, now what can we see here? For our first series, we have c, so some constant n, and the nth power x, if from infinity, 0 to infinity. Then for our second series, you have b of n, x of n, infinity, n equals 0. For the sake of showing what these are asking, I'm going to make this the same. Now we want to compare this series to series n is equal to 1, infinity, n times 7 times x of n minus 1. Right? Now what can we say about this? Well, the differences that you can notice is the starting number, n equals 1 versus n equals 0. So what does that change for us? We're here, when n starts at 0, you have the 0th coefficient and the 0th power. So you'll have a term that looks like just c of n. Here, when n is equal to 1, you'll have the first coefficient. So this will become 1 first coefficient, and then you have x to the 1 is 1, 0th power. So you still have the exact same format. Here you have the 0th coefficient, and then here you have the first coefficient, which makes sense because since these model Taylor series or Maclaurin series, if you have f at x equal to c of 1 plus c of 2 x plus c of 3x squared, right? Then what you have here is f prime at x is equal to the derivative of this, which is 0, plus derivative of this, which is c2, plus the derivative of this, which is c3x, right? So it makes sense that that first term cancels out, or it sort of disappears. Now, what else can we say? We also know that the radius of convergence of the derivative of a series and also the integral is the same, which means it has a radius of convergence between -10 and 10. I'm going to remove these brackets because we don't really know what happens at the edge points. So we'll show kind of like that. And the main concept here that's testing is that for you to recognize this series is the differential of this, or the differential of this is this. And then the second question relies on the fact that you also know that the integral of a series does not change its radius of convergence. So as you can see here, b of n, x of n, when you integrate it, is equal to, of course, b of n is a constant, so x of n, we'll say dx, is equal to b of n times x of n plus 1 over n plus 1, which is the basic formula for an integral of an nth power. And then you bring out the constants to one thing, and you get this, which is the same thing as original function, or original series. And again, since any x between 2 allows the series to converge, the same thing follows for here. You can do the proofing, you can do the ratio test on both of these, and you'll get the same answer, but you can do that on your own. Here it asks us to find a power series representation of the function and determine the interval of convergence. Okay, I will only do the interval of convergence for this half, and the other half here I'll do just the representations. Okay, now we have our first function as 1 over 1 plus x. Now the main underlying concept between this, or in this problem, is that you know that any function or series of the form, let's say a, b, c, can be transformed into the form b over 1 minus r, which hopefully you can recognize as the formula for radius of convergence of a geometric series. I think that's what it's called. So basically you kind of force your function to be a geometric series, or at least the number at which it converges to, right? So when we have here 1 over 1 plus x, you're saying that a value is equal to 1, but then your r value has to equal negative x, right? Why is that? Well, basically, if you look here, if you originally had 1 over 1 minus x, but then your thing here was negative x, then the negatives will cancel out and you get positive, right? So you're sort of forcing this term here to look like minus r, so that must mean the original was negative x, right? Because it had to be in this form. Okay, now knowing this, we can sort of work backwards. So that a geometric series is always in the form n equals, we'll say 0 to infinity of, it's always a times r to the n, right? Sorry, geometric, and it's also alternating, or it could be alternating, so we'll put in brackets. So here, since we have that, we can say that this is the series, and it starts at 0, goes to infinity, of 1 times negative x to the n. And if you look at this term here, you see that x to the n is equal to negative 1 times x to the n, which is equal to negative 1 to the n times x to the n, right? So then, now you see here that this is actually an alternating series. N equals 0 to infinity of negative 1 to the n to the n. All right, cool. Now let's look at this one. You have here 1 over 1 minus x squared. Again, we can recognize that a is equal to 1 and r is equal to negative x squared. Now working from this, we can make the series as infinite sum from n equals 0 to infinity of 1 times negative 1 to the n times x to the 2n, right? Or that's the same thing as saying x to the 2 times n, or to the power of n. Or you can end with that. That'll be the same thing. Now let's look here. Now we have 2 over 3 minus x. How do you do this? Well, the naive thing would be to follow the same order, but we have an issue here where we have a number 3 right here, right? And to overcome this error, by this kind of issue, we'll multiply the top and bottom by the reciprocal, so 1 over 3. Now we'll get that 2 over 3 over 3 over 3 minus x over 3, right? These will cancel out to give you 2 over 3 times 1 over 1 minus x over 3. Now you can clearly see that your first value, a, is equal to 2 over 3, and then your r is x over 3. Yeah, no, sorry, I made a mistake here. It should be positive. This is not an alternating series. Now we can transform this into the series form. N starts at 0 to infinity of 2 over 3 times x over 3 to the n. Now we have the question x squared over x to the 4 plus 16. Now again, the same issue here. where this is not 1, right? So how do we change that? We'll do the same trick we used. Multiply by the reciprocal. So 1 over x to the 4. Then we get x to the negative 2, we'll say, over 1 plus 16 over x to the 4. Right? Now we can say that, or we can extract that a is equal to 1 over x squared, that r is equal to negative 1 over 16 x to the 4. Now we know that this is alternating series test, or sorry, alternating series. Now you can make the series form. N is equal to 0 to infinity. A starts as 1 over x squared. Then you have negative 16. Now you can leave it like this or simplify further, where you can say, first of all, that n is equal to 0 to infinity. Of course, bring out the alternating part. Then you can say 1 over x squared. Then you can take out the fact that quartic root of 16 is 2. Let's see, actually. 2 times 2 is 4, 4 times 2 is 8. Yeah, it's 2. So basically, this is 2 to the 4 over x to the 4, power of n. Now, since we have a shared power on both, we can write that as, just here. We can write this as 2 over x to the 4 to the power of n, or preferably 2 over x to the power of 4n, right? Now you can do something else, where you take this term, combine them, where you have 1 over x squared times 1 over x to the 4n, and then this gives you 1 over x to the 4n plus 2. Or you can write it as 1 over x to the times plus 1. So that means your entire summation, entire series would be negative 1 to the n multiplied by 2 to the 4n all over x to the 2n plus 1. So something like this that looks super complicated can get broken down to here. So something you should remember is that if you got to this point on your own, then you can work backwards and get to this point, right? So if ever you get a problem where it tells you, given some sort of complicated function like this, go down to the function itself, it looks complicated at first here, but breaking it down to here and then going backwards is much easier. X minus 1 over x plus 2. Again, we'll do the reciprocal trick. So multiply top and bottom over x, because you recognize, again, that this term must be a 1, right? To follow the formula, where do you go? 1 minus a over 1 minus r. And then you get 1 minus 1 over x over 1 plus 2 over x. That your first value a is equal to 1 minus 1 over x, and that your r is equal to negative 2 over x. Because again, don't forget that this term here should be negative r. Right, now we extract from this the series. So n starts at 0. And another side note, n usually starts at 0. It might tell you when it shouldn't. A better indication is when n being 0 has an issue with your problem. So I'll show that. Now here, when n is equal to 0, you have the term 1 minus 1 over x times negative 2 over x to the 0, which goes down to 1, right? Now, if you had something like over n, this might be an issue. It might not always. Of course, series have the ability to have infinity. So 2 over 0 would give you infinity. Of course, you could have a series that starts infinity. It's weird, but that's possible. but sometimes you have asymptotes in your series if you think of them as functions. So maybe watch out for that. But I think the problem would usually tell you. So we'll simplify this again. Of course, n starts at 0, goes to infinity. And you have the alternating part. Then you have the constant 1 over x. Then you have, of course, 2 over x. Now, I guess you could expand this into here. Maybe you get a different term, but I think this looks fine. So you have x over 1 plus x. Amazing. Now, we can extract from here, without doing any work, that a is equal to x, and r is equal to negative x. Now, extract from here the series, n is equal to 0 to infinity. And then you have the alternating part, which you can pull out immediately. Then you have x, then x to the n. And of course, you can do a bit of simplification. So this is just x to the n plus 1. There you go. Now we need to find the radius of convergence. And you always know to get the radius of convergence, you must do the ratio test. So we'll start by stating we're doing the ratio test. We'll say for radius of convergence. Then we get that negative 1 to the n plus 1 times x to the n plus 2 over negative 1 to the n times x to the n plus 1. Okay. Now what do we get here? Of course, the absolute value. Now what do we do here? We can say that this cancels out with this. So you get left with, oh, well, the negative terms would cancel out because of the absolute value. Alright, so you have left with the limit as n approaches infinity of the absolute value of x to the n, x to the 2 over x to the n, x to the 1. These cancel out, this cancels out. This gives you limit as n approaches infinity of x. And then basically we force this behavior to converge. So we say this must be less than 1 for it to converge, which means the radius of convergence is between 1 and negative 1. So we extract that radius of convergence is equal to 1. Alright. Okay, let's see. Let's try a hard one. Let's do the last one, 12. So we have x plus a. So we'll basically generate a new formula for ourselves for any function or series in the form x to the x plus x squared plus a squared. Okay. Again, same tricks. You take the reciprocal 1 over x squared. Alright, and then you get 1 over x plus a over x squared over 1 plus, I'm going to simplify a bit, a over x. Right? Hopefully you can see how I did that. You would get the term a squared over x squared. The common power would be 2. So you get a over x to the power of 2. Now you can extract from here that a is equal to 1 over x plus a over x squared, which you can say is 1 over x times 1 over x times plus a over x. You don't need to do that, I just think it looks nicer. Now r must be the negative of a over x squared, because of course we have a positive term here. Now from this we extract our series to be n starts at 0, goes to infinity. Begin with the alternating term, then you go to the constants. 1 plus a over x. And again here, I took out the common factor of 1 over x because over x squared can be written as a over, and then you bring the term a to the x, a over x to the 2 to the n, but you can simplify that as 2n. Alright, now you must find the radius of convergence for this. So again, begin by stating you're taking the ratio for radius of convergence. Now you get, again, you're taking the limit as n approaches infinity of the absolute value of negative 1 to the n plus 1, we have 1 over x, 1 plus a over x, times a over x, 2n plus 2. I got this from the fact that it's going to be 2 times n plus 1, which is equal to 2n plus 2. Now, we can cancel out these automatically regardless of what's on the bottom because it's absolute value. These cancel out, and here you're left with only a over x to the 2. Right, so you have the limit as n approaches infinity, the absolute value, a over x to the 2, and then you force it to converge, so it must be less than 1. Then we basically get that a over x squared must be less than 1 and greater than negative 1. You should take the reciprocal, so there. Then you have x over a squared, because we need to get x in the middle, right? That's kind of the goal here. You can't have something like 1 over x must be less than 1, or no, we'll say b, right? That's not the basis of convergence. You need an x term here. That's what you should know. Now, we multiply both sides by a squared, and again here, it tells us that a is greater than 0. But regardless, that doesn't really matter to us. Actually, it does matter to us. Since a is always greater than 0, we can take the square root of this, and we get, oops, interesting. Okay, we'll multiply both sides. We'll get a squared, and then x squared, a squared. Okay. This is where you get something strange. We can still get the radius of convergence. It's just that here you'll have a I less than x a, right? Absolute value, but okay. So absolute value. Okay, you can forget about what I did here. Just look at this part here. You take the reciprocal again, same way as we did. X squared over a squared, still absolute value 1. Now here you have x squared less than a squared, then x must be less than a. And you don't have to show the absolute value because you took the square root of a square, because a is always greater than 0 because of this condition they give us. But what happened here is that because you have it between 1 and 1, you'll get some random thing here, some random complex number. Doesn't really matter. The radius of convergence you can get from this term here. You don't have to expand it out. This is only if you want to get the interval of convergence and also the radius. Okay, let's see here. Now it's asking us express the function as the sum of a power series by first using partial fractions. Okay, so the partial fraction concept tells us that if you ever have, let's see here, a over bx squared plus c, then this can be broken down to d over x plus b plus e over x plus c. So you can sort of undo what you did, or hypothetically did before. You know? So we have the function here, 2x over 4, or minus 4, x squared minus 4x plus 3. Now basically, if you were to look at this part here, you have 3 and 1, negative 3, negative 1. So you can break down this to 2 times x minus 2 over x minus 3, x minus 1. Nothing really cancels out, but you can write this as is equal to a over x minus 3 plus b over x minus 1. So we're attempting to find a and b. We'll multiply both sides by this denominator. We get that 2 times x minus 2 is equal to a times x minus 1 plus b times x plus 3, x minus 3. Okay. Now this means we have to find a in the most efficient way possible. You would either expand or say let x equal to some specific value that allows you to isolate a and b. That can be easily done by finding x to be equal to 1 and x to be equal to positive 3, because that immediately allows us to cancel these terms out. So if x is equal to 1, then you have 2, 1 minus 2 is equal to b1 minus 3. Right, so you have negative 2 is equal to negative 2b. Yep. So b is equal to 1. Yep. All right. And then here, if x is equal to 3, then you have 2 times 3 minus 2 is equal to a times 3 minus 1. Then you have 2 is equal to 2, a 2. Huh. Weird. Okay, works out pretty nicely. So a is also equal to 1. That's weird. Did I do that right? Yeah, I guess so. Okay. So that means we've simplified this to 1 over x minus 3 plus 1 over x minus 1. So now again, it wants us to describe this function. Again, this is still f at x. We haven't changed anything about it. We just manipulating it to look different. It wants to express it as a sum of power series, right? So we'll borrow from everything we just did in the last part. I'll just consider these two as two different series. Why? Because the definition of the series, along with the definition of the integral and the limit, allow us to have the sum of two terms equal a single series, which means if you have a series a of n plus the series b of n, you'll have a product series c of n, where c of n is equal to a of n plus b of n. The same so goes for the integral, because the integral borrows from the definition of the limit and series, where the integral of a at x plus the integral of b at x is equal to the integral of c at x, where c at x is equal to a at x plus b at x. And the same concept goes for the limit. So that means we can describe this function as two different series and then combine them into one term, c of n. So basically we can do a lot of it in our head because you did so much in the other question. Look at that, this series is equal to, from n to infinity, 1 times 3 to the n, right? So just 3 to the n, plus this series from n starts infinity to 0 of 1 to the n. Now, this means this entire function, f at x, is equal to, from n equals 0 to infinity, of 3 of n plus 1 of n. Maybe that'll be a bit harder. So we have here f at x is equal to 2x plus 3 over x squared plus 3x plus 2. And we have factors of 2 and 1. Oh yeah, 2 and 1. Okay, so here we get 2x plus 3 over x plus 2, x plus 1, because that's simplified as it goes. Now we want to convert this to the form, we use different coefficients, c over x plus 2 plus d over x plus 1. Now again, we'll do the same thing. We multiply both sides by the denominator. We get that 2x plus 3 is equal to c times x plus 1 plus d times x plus 2. Again, you can use any method of figuring out these constants that you like, but I think the best way to do it, especially with these, is besides expanding them out, we just say let x be two strategically chosen terms, or numbers, which would be -1 and -2, right? So if it's equal to -1, then we'll have that 2 -1 plus 3 is equal to c -1 plus 1, which goes to 0, plus d times -1 plus 2. Now here we get that it's 1 is equal to, okay, d is equal to 1. That makes no sense. It's too nice. Okay, we'll try and test that out. And then we get that. Here we get that's 2 times -2 plus 3 is equal to c times -2 plus 1 plus d times -2 plus 2, which again goes to 0, which means that you get here -4 plus 3 times c times -1. Weird. Okay, c is also 1. Ha. Okay. These seem to like it was too easily found. Okay, let's try something here. So we're claiming that these two terms is equal to. All right, let's test that out. So if you multiply, you get x plus 1 plus x plus 2 over x plus 2, x plus 1. The top term becomes 2x plus 3. Bottom term becomes x squared plus x plus 2x plus. Yeah, I guess that's correct. Weird. Those are like really nicely made questions. Okay, now that we've proven that to ourselves and we know we're correct, we'll compare these to the series again. Here this time we'll have two alternating series because these are both positive, and I'm going to skip some terms, but we can do them all as well, and it goes to 0 to infinity of -1 to the n, 2 to the n plus 1 to the n. And if you want to get like a broken down version of that, you basically have two series, both starting at 0 plus infinity. The first one would be -2 to the n, and the other one would be 0, infinity, -1 to the n. And that'll give you the same thing. I'll do the rest in part 2.